So just as a refresher of where we were at the end of class, we were trying to find what the electric field is at some distance x, and I don't know why I chose x, but I did, y, z, whatever, some distance x above a big plane of charge. We didn't talk about whether this plane was a conductor or an insulator yet, which is, for us, not something we really know enough about to do. So we're just assuming that the charge is uniformly distributed in a single plane of charge, but it's spread uniformly over that. So I guess I should probably note that this is a uniform charge distribution. And we're going to use this later in the year when we start talking about the idea of a capacitor, which is an electric device we put in a circuit. All right, well, what we had talked about with this was that near the surface of this, the electric field is going to be, because of our x is much, much less than the length idea, that near the surface it's kind of like looking at the surface of the Earth. Far away from the Earth looks round. Near the Earth's surface it looks flat. And so a field, gravitational field for the Earth is straight up and down near the Earth's surface. Same thing here. Our field is going to be directed straight away from this in a uniform field, uniform in direction, uniform in size. On the other hand, and so we're going to choose things so that we don't have to worry about the field fringing at all. That's different than when we looked at the curving of the Earth. So with that idea in mind, we tried to draw a Gaussian surface that would work for this. And what we came up with, the first idea that got suggested was draw some kind of rectangular prism. So this is the top of my rectangular prism. This is the beginning of a side. And this dotted green line stuff down here, this is the part of that same rectangular prism that's below it. So I'm extending a distance above and a distance below this rectangular, or this plane. My prism goes above and below that so that I've got flux through the bottom and flux through the top. Okay, we ran through our 3 rules for selecting Gaussian surfaces in class, and we decided that this met those 3 rules. So the first rule was, is E either parallel to dA or perpendicular to dA at all points on the surface? On the top surface and on the bottom surface, E is parallel to dA, so that's good. On the left, right, front, and back, E is totally perpendicular to dA, so that's going to make it so that there's no flux through those parts, so we're good. Second part, on the sides where we have flux, E is either uniform or E equals 0. E is going to be uniform across the top of this, again, because of our whole uniform field idea, kind of like extending from gravity. That idea, we're applying it to electric stuff, and it works. Okay. Third part with this, make sure that the area of our Gaussian surface is easy to calculate. You can't get much easier to calculate a surface area than a rectangular prism. That's about as easy as it gets. And we're going to show later, if we have time in this video, that actually any shape we choose, as long as it has a flat top and a flat bottom, would be equally good as a Gaussian surface. So we'll start with this rectangular prism and say, hey, this works. Okay, so just like we did yesterday, we're going to take this E dot dA thing, and we're going to break it up into a bunch of different sides so we can look at the flux through all those different aspects, all the different sides of this thing. So I'm going to do E dot dA for the top of this Gaussian surface. I'm going to add that to E dot dA for the bottom. And then I'll do E dot dA for the sides. And I'll do E dot dA for the front and back. So I'll just do FB for front and back. And that has to add up to how much charge is enclosed divided by E0. Okay, now I don't think I stated how much total charge is on this. So let's just say that the total charge is the very generic plus Q. Because I said it was some positive amount of charge, we'll just call that plus Q. And that this has to equal the net flux. Okay, now some of you may be looking at the integral part and say, why did he not draw the circles on there anymore? Well, because this closed surface is top, bottom, side, side, front, back. This integral broken up into different pieces adds up to that same top, bottom, front, back, side, side, but we've broken it up into each individual one. Each of these by itself is not a closed 3D shape, but if you add them all together, you get back to the closed 3D shape. So that's why that circle is no longer on that integral. All right, so then we want to start to look at these dot product things, and this is where understanding dot products is such a valuable thing. Do we have flux through the top? Is E parallel to dA through the top? Yes. So this part we want to keep. Do we have flux through the bottom? Is E parallel to dA on the bottom? Yes. So we want to keep that segment. What about E dotted with dA on the sides? Nope. There is no flux through the sides. So you can take that segment and send it off to Zeroville. E dotted with dA, that dot product is 0. And same with the front and back. Nothing useful there. So all we really care about is the flux through the top and the flux through the bottom. All right. We chose this top and bottom so the electric field was a constant. We've already taken care of the fact that the dot product is going to be so that we can take the whole E times that dA. So this integral quickly becomes E times the integral of dA for the top. I got rid of the vector nature because all that is to check to make sure they're parallel to each other. I've got the bottom side there, and I'm going to do E dotted with dA for the bottom, only I'm not going to write the dot product anymore. And being silly, I should pull the E out because the E is constant across the bottom surface as well. So I'm really just integrating the area for the top and the area for the bottom, and that equals charge enclosed over E0. Okay, well we know that E is E, dA integrates to A, so this is E times the area of the top plus E times the area of the bottom is equal to how much charge is enclosed divided by E0. Okay, on that area top, area bottom, and charge enclosed part, this is again where you have options about how you want to do this. Some books are going to draw it so that their Gaussian surface actually extends all the way out across the whole surface area of this plane. I don't like to do that for the same reason I didn't like to do it yesterday. I don't like to do that because if you're thinking about the electric field due to a plane, it's pretty uniform in the middle, but as you get towards the edges, you'd start to have a little fringing. Okay, and so I don't like that approximation. I don't like the fact that it fringes towards the edges. And I have an easier time buying that my field is uniform if I'm only drawing this Gaussian surface for portions, not just, not only right at the middle, but for a portion of this. So I don't have to worry about the fringing of the field at the outer edges. So for me, I'm not going to treat it as though my Gaussian surface goes all the way to the edge. And for that reason, my charge enclosed is not going to be all of this plus Q. Okay, actually, maybe I'll just show you both ways to do it. Method 1 would be the Gaussian surface extends across the whole plane. Okay, and the result-wise, it's going to be the same either way. So then my area is just going to be L squared for the top, and it's going to be L squared for the bottom. And how much charge is enclosed? Plus Q, and that's all over E0. And so my electric field is going to be 2 times E times L squared plus Q, equals Q over E0. And so my electric field in the end comes out to be Q over L squared, which is basically the charge over the area times E0. Okay, so it's really charge per area over E0. The other way to do it is the way I, again, prefer. Use a proportion. Figure out what portion of that area is actually enclosed. So for me, I would say that E times the area of the top plus E times the area of the bottom is equal to, and for my Q enclosed, I'm going to set up a proportion. I'm going to say that Q total is my whole charge over area total L squared. And that's equal to the amount of charge I have enclosed over the area I have enclosed. So that plus Q over L squared times the area I have enclosed is equal to my charge enclosed. Okay, so I'm using my favorite tactic of setting up a proportion again. If I plug that in, Q over L squared times area enclosed over E0, I'm going to end up in exactly the same place as I did when I did it this way. Why? Because if I look at the area on my charge plate that has charge on it, So that would be like an area in the plane of about this big. That area is exactly the same as the area of my top and exactly the same as the area of my bottom of my Gaussian surface. So if I factored out an area and then canceled out, these areas cancel out. Maybe I'll write that out so you can see exactly what I mean. This would be E times area top, this would be E times area top plus area bottom equals what we had there. Our top area, the area of the top of my prism, and the area of my bottom of my prism are the same. So this is E times 2 of that area. But that area, the area of the top of this, is the same as the area that is enclosed that has charge on it. So that equals Q over L squared A over E0, and that's the area I was canceling out. So I end up with exactly the same thing, that E is Q over 2 L squared E0. Here, I lost a 2, idiot. So E equals Q over 2 L squared E0. You may have been yelling at me the whole time on the video saying, where's the 2, where's the 2? Well, I forgot it, but there it is. So that fixes it. Okay, so we are finding electric field for this thing does not really have a dependence upon how far above we are. We're treating it as though it is a uniform field as we move away from here. That makes sense. It's kind of like a gravitational field. We don't say near the Earth's surface that the gravitational field here is different in strength than up here. Okay, we just say G is 9.8 meters per second squared everywhere, and that 9.8 just depends on the source of the gravity. Same thing here. We're saying this electric field does not have a height dependence, that this electric field is the same as uniform, not diverging, staying constant in direction, staying constant in size, near that plane. And so it's Q over 2 L squared E0. That's why we're saying that. A lot of people get angry saying, I want this to depend on how high above. Well, think about gravity. We don't make gravity change on how high we are above the Earth's surface until we get really high. Same thing with this electric field. As long as we're staying really close to the surface of this charged plate, our electric field should not have a height dependence. All right, that's the end of this video.